chapter 7 is going to start the progression into being able to deal with a concept called similarity. In the course, there's really 3 topics that underlie this course. Equality, congruence, and then similarity. Okay? Those are really the 3 kind of ideas that govern our topics and what we've done with triangles. We've shown, equality deals solely with stating that 2 measurements are equal. But then congruence, we talked about how shapes, if they're the same size and same shape, then they're congruent. Proportionality is going to, it kind of links back to the same thing that equality had. So for things to be congruent, we needed equality amongst parts, right? Well, we're going to find out for things to be similar, we need proportionality between corresponding parts. So that's what this chapter is going to kind of lay the groundwork for. The first thing we need to do is define some terms, though. Okay. First one, which is ratio. Okay. So a ratio is the compare. I don't know if I really like this definition, so I'll give you a couple different ones here. So the ratio of one number to another is the quotient when the first number is divided by the second. Okay, so a lot of times fractions are set up that way. Okay, if you think about rational numbers back in algebra are defined as numbers written as a over b. Okay, a over b of a divided by b, where b cannot be 0. Well, what's the root word for rational? Ratio. Okay. I like the definition that it's a comparison of 2 numbers through division. You're gonna hear me say that a lot. The comparison of 2 numbers through division. A couple different ways that you guys have seen. So this stuff should not be entirely new to you. You talked about ratios and proportions last year's entire unit on ratios and proportions in algebra. So you may have seen this notation. Okay, we can say I can only compare 3 to 9. Compare it as the phrase 3 to 9. But we prefer, obviously, with the word in there. The mathematics is not all that conducive to having words in our notation. So then we compare as 3 over 9, 3 divided by 9. And then more formally, we prefer it to be reduced. Okay, you've also probably seen it written this way. Don't know why that disappears. 3 what in the world? There they are. That's awesome. All right, 3 colon 9. You've seen that before, right? Okay. Understand the way that I compare 3 to 9 is different than comparing 9 to 3. Correct? So order when we do comparison through division is important. And that's because division is not what, or does not carry what property? Commutative. Okay, so division is not commutative, so 3 compared to 9 is different than 9 compared to 3. We want to take into account, like in Math Excel, they're going to make sure, or they want you to write your ratios in simplest form. And I ask you to abide by that just for your sake of getting those questions right. The one thing that you're going to find out, though, that there will be times, at least when setting our problems up, that simplified ratios aren't as informative as the unsimplified. So when I set things up in a proportion, I might not simplify them right off the bat. Does that make sense? I usually won't simplify my ratios until I'm done with the problem. So here's just a couple things that we can do, just getting the hang of ratios, okay? We might want to compare the ratio of AC to BD. AC to BD. Okay, so that's comparing two lengths. AC's length is 6R. BD's length is 20. So we write it that way. People quit bugging me with my phone.
Do you care which way we write it? Like the semicolon?
No. Just be, so the question is, can I write it that way? Can I write it that way? Either one is fine. Just be cautious on like your homework, because your homework's probably 99% of the time going to ask you for that one. Because they both have a factor of 2 in them, the simplified version would be what, 3R over 10, or 3R compared to 10 that way. Is that okay? Angle C compared to angle D. Angle C is 80 compared to D, which is 40. If you want to write it as 80 colon 40. But those both go to 2 or 1, or 2 compared to 1. Okay? When talking about ratios, we still view this, 2 to 1. Writing it as a fraction, a lot of times, well, denominator is 1, so I just write it as 2, right? But when talking about comparing like objects, we still want to have that 1 visible. Okay? It basically refers to the idea that angle C is 2 times as big as 1 angle D, or 2 angle C's will make 1 angle D. Does that kind of make sense? Actually, I said that backwards. 2 angle D's will make 1 angle C. So that 2 to 1 tells you that relationship. Some questions you might see them ask you comparison of 2 things in which one of those you do not know, other than through the use of previous theorems. Okay, so I don't know angle B right now, right? But how many degrees should there be in this quadrilateral? 360, right? So if I go 360 minus 110 minus 80 minus 40, that should get me angle B, right? Okay, so what is that? 120, 230, is that 130? Okay, so angle B is 130 degrees. So now if I compare B to D, so B is 130, D is 40, okay, or 130 compared to 40, and those both reduce to like 13 over 4, or 13 colon 4, however you may want to write it. Okay, but understand 13 to 4 is different than 4 to 13, right? Okay, so just be on the lookout for the order. It says to compare objects with ratios, the measurements need to be in the same units, okay, if at all possible, okay? So we like to compare inches to inches, feet to feet, miles to miles, grams to grams, milliliters, milliliters, that kind of thing, okay? It's not always possible. Sometimes we compare dollars to hours, okay? And we get what we call a rate, okay? If I, does anybody have a job? How much you make an hour? $12 an hour. $12 is the top number compared to 1 hour being your bottom number, right? Okay. So that's called, and working, that's our hourly rate. Rate coming back to ratios. Does that make sense? Okay. But if we can, we would like things to be in the same units. Okay. This is a question that kind of exemplifies that and kind of explains why we would want that. It says write a ratio. It says bonsai. You guys know what bonsai trees are? Yeah. Okay, so like those little miniature trees that, they live for a long time, but you manicure them, and a lot of people keep them inside their houses, that kind of thing. Okay. It says the bonsai bullet cypress tree is a small version of a full-size tree. A Florida bullet cypress tree called the Senator stands 118 feet tall. says, what is the ratio of the height of the bonsai to the height of the senator? Okay, so we're going bonsai. So what I like to do a lot of times when they ask me questions like this, I like to first write down in words or some type of notation the order that I'm comparing. So I'm comparing the bonsai to the senator. Okay, that's what the overall question here is. Okay, now the bonsai tree we see here is 15 inches. The senator is 118 feet. Okay. Now, we have a problem with that because the units are different, right? When they're different, we want to look at them and say, okay, is there a link between one and the other? Okay? And because it's inches and feet, there is a link, and that link is a two-way street. So you can change your feet into inches, or you can change inches into feet. It's up to you, but which would be easier? Feet and inches. Because feet and inches, you have to do what operation? Multiplication, right? Okay. If I have 118 feet, there's 12 inches for every one of those. So that's going to give me 1416. So now, since the units are the same, we have 15 compared to 1416. They both divide by 3. So it gives me 5 over 472. Okay, now it's not, you could go the other route. Okay, so that was changing everything to inches. But let's change this 15 inches to feet. How do I get inches into feet? Divide by 12, right? Okay. So when I divide that by 12, I'm going to get 1 foot, right? But 3 inches left over. Well, if I have 3 inches left over out of 12, that's a fourth, right? So 0.25. Just going to write it that way right now. Now they'd both be in feet. Okay? Now you might see that these two numbers obviously are different in their formatting, but if we type in 5 divided by 472, and then 1.25 divided by 118, is it the same decimal? Okay. But if I didn't change things, if I would have left it as 15 inches over 118 feet, that is different, right? And that's because this was inches over feet, and those don't work together in that comparison. Does that make sense, everybody? Questions on that? Is that something we knew? Extended ratios are a thing. So I'm not just limited to comparing 2 objects. We can compare 3 objects, 4 objects, 5 objects, however we want to. Okay. Now the way that we write them in fraction form is a little bit messier. Okay. This format, when we have an extended ratio, the convenience lays in using the colon. Okay? So when I have 3 things that I want to compare, A to B to C is how I'd read that. Basically what we're doing is saying that not only are you going to compare A to B, like we have here, but you can also compare A to C, and then you compare B to C. Okay? And what that does is that creates all 3 possible comparisons in that order. There's no way for us to write, like if I have Like I can't write this in a fraction notation. But once I break them down into the individual comparisons, I can write that as A over B, B over C, and A over C.
Isn't there a property that do the same thing?
Say it again.
Isn't there a property that do like the same thing? Like it took me like A B plus B C plus A C.
I think you're thinking about the transitive property that said like if A equals B and B equals C, then A equals C. Kinda. But we're not saying that these are all going to be the same. These could all be different fractions. It's just right now a notation thing. So if I had, let's do one with 4. So if I had A compared to B, compared to C, compared to D, basically to find these 3 things, in this case it's going to be more than 3, you're going to take A, you take your first term, and you compare it to everything else. So B, and then A compared to C, and then A compared to D. Then you're going to take the next one, which is B, and compare that to C, and compare that then to D. Okay? A lot of times you can go back and compare it to A. You can say B compared to A. But if I have B compared to A, here I had A compared to B, right? So the only thing that they're going to be is reciprocals of one another. So a lot of times, if it's 4 parts, you just do, I hit B and compare it to the things that are to the right of it. Now I'm going to go to C, compare it to the things that are to the right of it, and that should then be the comparison of everything. Does that kind of make sense? We'll mainly do, and we don't see too many problems overall with extended ratios, but if we do, it'll most likely be with just 3 parts. Here's kind of an example where extended ratios come into play. Basically, what they tell us is that you've got and this is usually going to be the case all the time. Extended ratios are going to be provided to you as simplified ratios. So they're saying that the sides of this triangle are in a simplified ratio of 4 to 6 to 9. They tell you that the perimeter is 190 units. So they want to know, well, if that's the case, then what is the actual length of these segments? Okay? So let's say this one was the 4, let's say this one was the 6, and let's say this one was the 9. Okay? Now, that's a simplified ratio because if one of them is a length of 4, the other one's the length of 6, the other one's the length of 9, that only adds up to 19, right? Okay? So those cannot be the 3 sides of the triangle. Okay? And right away, I think maybe some of you can already see what the answer is, but I want to talk about this a little bit more in depth than just going straight to the answer here. If they are 4, 6, and 9, but those are reduced, that means each value was reduced that those 4, 6, and 9s came from. So there's 3 unknown values here, and they all got reduced. And when they get reduced by the same factor. So let's say that these things got reduced by a 2. So let's say instead of being 4, 6, and 9, they were actually 8, 12, and 18. That's still a 4, 6, 9 ratio, right? But 8, 12, and 18, that sums up to what? 38? Closer to 190, but they're still not the right ones, right? So maybe they were all simplified by 3. So instead of 4, it was 12. Instead of 6, it was 18. Instead of 9, it was 27. And add those up. They don't get 190, right? Do you see how we can keep playing this game? Say, well, what if it was a factor of 4, so 16, 24, 36, and add those up. We don't know what that factor that they were reduced by was, right? So if we don't know what that factor was, instead of saying 4 times 2, or 4 times 3, or 4 times 4, if I don't know the factor, what could I say? 4 times x. And now if they were all reduced by the same factor, then that x Should have been in all of them, right? Now think about this. If I look at like 4x compared to 6x compared to 9x, they all can take the x out and we have 4, 6, to 9, right? Okay. But to find out what that specific number was for x, I have to know what perimeter is. Perimeter is adding up all the side lengths, right? So one side length would have been 4x, one would have been 6x, one would have been 9x, correct? They total 190. 19xn is equal to 190. Xn is 10, correct? So if x was 10, that was the factor that was broken out of or taken out of the 40, the 60, and 90 to get us to the simplified extended ratio of 469. Okay? So you might see questions like that. Sometimes they talk about triangles. Next question could be a quadrilateral. Next one could be a pentagon. Doesn't always have to be talking about perimeter. Okay, but that's kind of the idea that we get with extended ratios. Any questions on that or anything like that, or any confusion about anything yet? All right, so let's talk about proportions. Understanding proportions is going to be the number one thing that's going to allow you to be proficient in everything else that we talked about for probably about 2.5 months. All right, so an equation stating that two ratios are equal is called a proportion. An equation stating that two ratios are equal is called a proportion. So the equivalent fractions set equal to each other form a proportion. So we've seen this before. Okay? In its simplest version, we see down here, a lot of times what you guys would have started with was like the 12/15ths. And because they both have a factor of 3, and you would take the 3 out and you would get 4/5, right? That is a proportion. Okay? You a lot of times maybe didn't write or maybe know all 4 terms. So where you guys have used proportions is usually solving like cross multiplying. You've heard that before, right? To solve for a variable. But if I know all 4 terms, both numerators, both denominators, it's usually because, or I usually don't maybe have written the proportion down like this. You've dealt with proportions like 2/4. If I see 2/4, what do I type that in as an answer? 1/2. So you could change it straight to 1/2. You never wrote it as a proportion, right? But it is a proportion. Okay. And the reason for that is, if I take in 12/15ths as a decimal, 4/5 as a decimal, they both give me back 0.8. Okay, they are equal. Okay, it says every proportion has 2 cross products. These products are equal. Okay, so if something is a true proportion, I should be able to take that product. So what's 15 times 4? 60. And I should be able to take that product. What's 12 times 5? 60. And that should always be true if the 2 ratios are indeed equal. If the ratios are unequal, those 2 products will be unequal. Does that make sense? And then you would not have a proportion. That logic right there, that concept, is what allows us to cross multiply to solve for variables in proportions. Okay? Here in words, we're seeing that for any numbers, this is basically talking about that cross products are equal. It says for any numbers A and C, okay, and any non-zero numbers B and D. Why do they have to be non-zero numbers? Okay, you cannot divide by 0. Okay. If I cross multiply these, what we're saying then is that A times D will always be the same thing as B times C. Okay? And that is stuck together with an if and only if statement. So it's a biconditional. So meaning you can start with that side and actually get to that side if you want or if you need to. Okay, so it's a two-way street. Start with the two ratios equal each other, or you can start with the two products equal each other. But with that saying, if I gave you, we had, what do we have? We had 5 over 472. This is with the bonsai question. Change the size of my marker here. We had 5 over 472, and that was when we changed things into inches, I believe. Okay. We also then had 1.25 over 118, and that was when we changed things into feet. If I want to see if those are equal, all I have to do is take those two numbers, multiply them together. So 472 times 1.25, and it gives me 590. What am I going to get when I take 5 times 118? 590 again. Okay, so that confirms to me, because if you remember what we did, I think I still have it here. We changed them both to decimal version and compared them that way, right? Well, if you want to do that, if you didn't have access to a calculator, and you want to do that division, you're gonna be spending some time with that division algorithm coming up with this. Because we can multiply a lot quicker. We can check to see if these are equivalent by just multiplying the cross products. Okay. Now, you're going to hear me talk about some things that are not necessary. I'm not going to use the terminology very often as cross product. Okay, that's more of a 7th grade, 8th grade term. We use the higher level terms for you. Okay. So it's an equation that states that two ratios are equal. It's called a proportion. We already know that. Okay. When we talk about the 4 parts of our proportion, you have 2 numerators and 2 denominators, right? Okay. And when we do cross products, we pair one numerator with one denominator, and one denominator with the other numerator. Okay. If we talk about them in being compared, like the notation with semicolons, okay, that number right there, so that'd be the first number I say in the entire statement. 2 to 3, or 2 compared to 3 is equals 4 compared to 6. 6 would be the last thing I say. Okay? The first and the last things, and think about on a scale, on temperature, okay, on a thermometer, okay? The first value all the way at the bottom of the thermometer, and the top value all the way at the top of the thermometer. The bottom one will be very, very, very cold, right? The top one will be very, 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 very hot, right? When it's very, very, very cold outside or very, very, very hot outside, they refer to those temperatures as extremes, don't they? Extreme temperatures, does that make sense? Okay, because they're at the far ends of things, okay? That's the way I remember which of these sets of terms are extremes. They're the ones at the far end. They're the first and the last, okay? When you write this out or you verbalize it to yourself, the first and last objects that you say are the extremes. Okay? When we refer to means, okay, we usually refer in means average, right? Okay? And that idea concept kind of puts you in the middle. Okay? So that's kind of how I remember which terms in the proportion are what we call our means, okay? Mean or average is a measurement of middle, okay? If we're in a stats class, that's how we refer to it. So that being said, when I write it as this notation, which you will never write it this way, okay? But 2 compared to 3, it changes into 2/3. And 4 compared to 6 changes into 4/6. But if I read that, 2/3 equals 4/6 is 2 the first thing you said and 6 the last thing you said. So 2 and 6 are your extremes. If you can identify your extremes, then everything else is your means. So 3 and 4 are your means. So our textbook does not ever use the word cross product in it. Our textbook says the product of the extremes is equal to the product of the means. Okay? The product of the extremes equals the product of the means. Okay? And that's provided that B and D, your denominators, are non-zero value. Okay? So for example, another example there says 2/3 equals 4/6. Well, that's true because 2 times 6 is 12, and 3 times 4 is 12. Because the means product is the same as the extremes product, that's a true proportion. Okay, so see kind of an application of this. And I've got this. You can either use this. We can do this several different ways. I don't think I'm going to use that structure, so let's just wipe that out right now. So the twin jet airplane has a length of 78 meters and a wingspan of 90 meters. A toy model is made of proportion to the real airplane. The wingspan of the toy is 36 centimeters. Find the length of the toy. Okay? So if you've ever gone into like Hobby Lobby or anything like that, people that make or put together like model airplanes, model cars, that kind of stuff, as a hobby, like all the boxes that you would go and look at to purchase, they will have a scale on them. They'll say this is like a 36-to-1, meaning that every part in there is 36 times smaller than what it would be on the actual object, the actual car or airplane or whatever. Does that make sense? Okay. Everything's shrunk by a factor of 36. Here, they actually want us to they don't tell us that it's like 36-to-1 or 2-to-1 or anything like that, but we can figure that out using some of the information they give us. Okay. Now there's several different ways you can do this, but I like when I set up my proportions, and it's totally up to you, but I like to have in my numerators and you're going to find this to be very useful when we get to dealing with triangles and pentagons and octagons and other shapes. I like my numerators to be from the same object. Okay? So my numerators are going to both be from, let's say, the plane here. Okay? So let's say it says the airplane has a length of 78 meters. Okay? So I'm going to say length here of the plane. And over here, since I'm going to I want that to come from the actual plane, I want this to come from the actual plane as well. Okay? So here, the other measurement that comes from the actual plane is the wingspan, right? That's how I like to do things. Okay? On the bottom here, then, the length of the plane, there needs to be a connection between the numerator and denominator. The connection between these numerators was that they came from the same shape. The connection between these two things is that they're both going to be a length. Does that make sense? So it's going to say length of the toy or the model. And this here will say wingspan of the model. Okay? That's the way I like to do it. Okay? But that's not the only way you can do it. All right? And the reason there are alternatives to this, let's do this real quick. Let's say I gave you just A over B equals C over D, right? That led us to saying that AD was equal to BC. Is everybody okay with that? Okay. Well, can I write it this way? Can I say A over C? So all I'm going to do is I'm going to flip-flop these two. So A over C is equal to B over D. If I cross-multiply those, do I still get AD if I multiply those two? Do I still get BC when I multiply those two. And the reason I can do that is because multiplication is commutative, right? So when I'm doing this, I'm going to be multiplying these two. Let me highlight these. I'm going to be multiplying these blue ones. And I'm going to be multiplying these green ones. So as long as that product still is maintained, it doesn't matter whether I flip-flop the green ones. So I could write here wingspan of model over length of toy is equal to wingspan of plane over length of plane. That would be a viable way of setting up this proportion. Now, if I go across the top, is there an idea that links the top in two numerators? They're not coming from the same shape now. One comes from the model, one comes from the plane, but they're both wingspan across the top, right? Now, if I look at just one ratio, okay, I don't know why I use model and toy be the same thing, right? Here, they both come from the toy or the model. Here, they both come from the actual plane, right? So if you set up your proportion this way, you'd be perfectly fine, okay? And like I said, that was what I interchanged, those two, okay? Some people will say, I'm going to write it as length of plane over wingspan of plane. And then on the right-hand side, so all I'm doing is I'm starting with this one, length of plane, length of plane. I've flip-flopped these two. So here's going to say length of toy divided by wingspan of toy. And that will generate the same exact results. Does that make sense to everybody? Okay, so you have options here. And that's kind of I think it's kind of somewhat a kind of catch-22 sometimes in this course, or an issue that people have is like, Mr. Fay, I got the same answer, but I didn't write down the exact same proportion you did. Well, because multiplication is commutative, there's a lot of different proportions that could be written that still yield the same answer. Okay, so as we put these things in, I'm going to say, so go ahead and do all of these and hopefully prove that point to you. So the length of the plane was 78, right? So let's see here. All right, 78 there. Come down here. Right, 78 there. And length of plane, 78 there. Wingspan of plane was 90. I don't like that. Okay. And then we say if the wingspan of the toy is 36, so wingspan toy is 36 centimeters. Wingspan of toy 36 centimeters. Wingspan of toy 36 centimeters. When I cross multiply, we'll always get 78 times 36 in that one, 78 times 36 in that one, 78 times 36 in that one. That make sense? Okay. The other one, so I'm looking for the length of the toy, so that's going to be my variable, x. And when I cross multiply there, I'm going to have 90 times x. Okay. Now, there's a couple things here when we do this. So it's 78 centimeters. Or sorry, I guess that was meters, right? Kind of talk about the units here. And units usually end up being things that make people struggle because they neglect them when they do their algebra. And this might be something that you guys have recognized in maybe a chemistry class. If you neglect your units when you do your algebra, you might be 1, 2, 3 decimal places off in your answer. You might have the exact same, the right numbers, your decimal places just shifted incorrectly. Okay? So right now, if I do this, think about the answer that I want. It says I want the wingspan of, I want the length of the toy, right? Should my length of my toy, do you think I should have an answer in meters or an answer in centimeters? Centimeters, right? Let's think about, let's go through here and do the multiplication and see what happens here. Okay? If I go and take 78 times 36, so 78 times 36 gives me 2808. So those two right there multiply together give me 2808. These two together are going to give me 90x, right? Okay. So I have 90x equals 2808. Now, I've left a little gap here with the 90x because what was the unit on 90? Meters, right? What would have been, when I did this multiplication here, my units would have been meters times centimeters. Does that make sense? When I want to solve for x, you're going to divide both sides of here by 90 meters, correct? So 90s cancel and the meters cancel. Come over here, divide by 90 meters, the meters cancel, and the 2808 divided by 90, just give that as a decimal here, 31.2. See, x equals 31.2, but what is the only unit left over here? Centimeters. Does that kind of make sense? Now, if you're a person that completely wants to disregard that algebra with your units, what could you do? If I have 90 meters right here, how many centimeters is that? King Henry died by drinking chocolate milk, right? If we're at centimeters, and I want to know how many meters, I got to move decimal place 2 spots, right? Okay. I guess I'm standing at meters, and I want to go to centimeters, so you got to move 2 spots to the right. So 90 meters is 9,000 centimeters, right? Okay. 78 meters is 7,800 centimeters. Okay. Now if I cross multiply, so I go 36 times 6 or 7,800. It's going to give me 2,80800. And when I multiply these two, it's going to give me 9,000. Well, when I cancel those two, I'm back to multiplying, or dividing, I guess, 2,808 by 90. It's the same thing as I had over here, right? So if you don't like I said, if you don't like we call this unit analysis down here. If you don't like that, that's fine. Change everything to the same unit if it's possible. Change everything to centimeters or change everything to meters, and you'll be fine. If this is 31.2 centimeters, how many meters is that? If I'm in centimeters and I want to go to meters, I got 2 to the left, right? So move my decimal 2 to the left and I get 0.312 meters. Okay. We'll stop there for today. No homework tonight.